Hello everyone. In this video, we will understand one of the important interview question which is based on the bitwise manipulation. So let's start and see what is the question. So let's say you are given a decimal number, okay? And you have to tell whether that given decimal number is even or odd, okay? And you have to tell it using the bitwise operator, okay? So for example, you are given number 3. So you know 3 is an odd number. If number is 10, then you know it is an even number. 14 is an even number, and same way 11 is an odd number. Okay, so we know if a number is divided by 2 and if we get the remainder as 0, then that given number is even number, and if we get the remainder as 1, then that number is odd number. Okay, we know this thing, but we do not have to use this modulus operator. We have to use the bitwise operators, and then we have to tell whether this given number n is a even or odd. Okay, so this is the question. So same output we should get whether a number is even or odd, but we do not have to use this modulus operator. We have to use the bitwise operators. So we will see 4 different approaches to solve this question. Basically all these 4 approaches, they are not directly different. They are basically more or less similar. Okay, so we will see these 4 approaches one by one to solve this question. Okay, so let's start. Now to solve any question using the bitwise operator, we know that we have to deal with the bitwise representation of our input, right? So for example, this 3 is an odd number, as we know. So how we can represent this 3 in binary form? As 1 1, right? 1 0, that is 10. 10 can be represented in the binary form as 1 0 1 0. 14, which is an even number, it can be written as 1 1 1 0 in the binary form. Okay, or you can say this binary form, right? And 11, which is a decimal number, it can be represented as 1 0 1 0 in the binary form, right? Now to solve this these questions which are based on the bitwise operators, we have to come with the 2 things basically. Like one is the which bitwise operator we are going to use, like bitwise AND or JOR, complement. Okay, and the second thing we have to come with is like what will be the mask. Okay, what will be the bit pattern that we will be like applying on this given number, or you can say on the bit representation of this given number. Okay, so these are the like most important things that we have to come across, or you can say we have to find to solve the question using the bitwise operators, right? Now the next thing is to come with this, like which operator we have to use, which mask we have to use to solve the question. We have to come with some observation, right? So observation will differ from question to question. For example, in this question, if you see that this 3, which is an odd number, it can be represented as 1 1. Now here you see the this is the least significant bit, or you can say this is the 0th bit. Okay, so this 0th bit is 1. Now if you see any even number, like this is the even number, this is the even number. Okay, so 10 is an even number, and if you see the 0th bit is 0, or you can say the least significant bit is 0. Same 14, which is an even number, here also the 0th bit of this 14, that is the LSB, least significant bit, it is 0. While in the other case, that is 11, which is an odd number, the least significant bit, that is 0th bit, it is 1. So we saw that for any odd number, okay, for any odd number, the LSB, okay, the LSB, it will be 1. And for any even number, the LSB, that is 0th bit, it will be 0. So this is the observation. The odd number has least significant bit as 1, and even number has LSB as 0. Okay. Now the next question is how to know if the LSB is 1 or 0 for a given input number. Okay. Now how to know this basically, or you can say in the program, or you can say like what we should do. Here we are just seeing, okay, we are just seeing that LSB is 1 or 0. But if we have to find using a general algorithm, how we can do, like which operator we will use, right? So here I will use the bitwise AND operator. Okay, I will tell you that we can use the bitwise OR operator also and bitwise JOR operator also, but here let's start with the first approach. Okay, so as we know, when we use this approach, that n mod 2 equal to 0, we can get remainder as 0 or 1, because by 2 means we can get value as 0 or 1. If we do like n mod let's say 4, okay, then what will be the possible values of the remainder? We can get 0 1 2 3. Okay, this is like normal mathematics. Okay, now here also we have to use that thing only. Okay, like what is the thing? Basically we have to see that we have to use AND operator, as I told you. Okay, now here we have to see what will be the mask that we have to apply, right? So let's say if I apply 1, okay, like my given number is 11, okay, and if I take the mask as 1, okay, 1, so 1 can be represented in the binary form as 0001, right? And we are taking this example of the n equal to 11, that is the odd number, okay. Now if I do the AND, okay, bitwise AND on this, what I will get? So basically all these 3 bits of the mask is 0, okay, they are 0, then all these bits will become 0, okay, because I am applying the AND, okay, 1 0 is 0, 0 0 0, and 1 0, by applying the bitwise AND will be 0. Now the last bit, okay, because this mask is 1, okay, and here also it is 1, then 1 and 1, the bitwise AND will give me 1, right? So I got what? This is basically 1 in the decimal, okay, this is basically in the binary form, and in the decimal form it is basically 1. Now if we apply the same thing on the even number or any even number, let's say we take n equal to 14, even number, okay, and now we apply the AND operator, and the mask I took 1, okay. Now what I am doing, I am basically applying this mask as 1, and I am just observing what will be the value of this 0th bit basically, okay. So let's see, now all these bits are 0, so all these bits will become 0 0 0, okay, using the bitwise AND, okay, 1 0 bitwise AND will give 0, okay, and so on. Now if I apply this 1 on this 0 and I apply the bitwise AND, what I will get? The resultant bit I will get 0, right? This we already know, okay. I hope you know that how this bitwise AND actually works, okay. We will get answer as 1 only when both the bits are 1, otherwise we will get 0 only, right? So what is this number? Basically in decimal this is 0, right? So if we check any other even number also, like this 1010 also 1010, and if we apply this 1, okay, and bitwise AND, what we will get? Here it is 0, okay, we apply 1 on this, we will get 0 only, and all the other bits are 0, so we will get 0 only as the answer, okay. So and if this bit is 1, that means this given number is odd number, then in that case applying the bitwise AND, it will give me 1 1 means 1, I will get 1 0 0 0. So you come across the observation that if I apply the bitwise AND and use this mask, then I will get 1 only in the case when my given number is odd number, and I will get the resultant answer as 0 if I apply the bitwise AND with the given number and give this mask, right? So this is the observation. So this is the simple program using this approach, okay. So basically we are taking the number and we are checking if this operation, basically the number and the bitwise AND with the 1, okay, we are getting this answer, this answer we are getting as 1, okay. Basically you can write this way also, okay. If we are getting the final answer as 1, then we are saying that my given number is odd number. If I am getting 0, okay, if I am getting n bitwise AND 1 equal 0, then I will say my given number was even number. Simple, okay. So we can run this program and we can check the answer. So I compile and execute this program. Now if I say 11, which is an odd number, it is an odd number, yes. Now if I say 14, yes, it is even number. And if I take any other number, let's say 9 is an odd number, yes, it is an odd number. Same way you can check for any other number, let's say 0 is an odd, even number, so yes, it is even number, okay. So this is the program, okay. So I hope you have understood the program, okay. So the basic idea was we have to concentrate on the 0th bit, okay, and somehow we have to differentiate based on the 0th bit, okay. So if we apply these operation, we will get 1 in the case of odd number, and we will get 0 as the resultant answer in case of the even number. The next approach I will tell you using the bitwise OR operator, okay. So basically in bitwise OR operator, it will not be direct as we have seen in the previous approach. It will be like we will use the bitwise operator but with a twist. Observation will be somewhat different, okay. So like here same things we are having, same example, we will use the same examples, and I will first tell you the observation. So basically if I am given this, let's say n equal to 11, okay, so n equal to 11 means 1011, right? So basically this is given here also, I'm explaining here also, okay. Now if I apply this, see, and if I am given this number as 14 is basically a even number, so this is 1110 is a basically 14, that is binary representation, and this is the mask 0001, and I am applying the bitwise OR operator, right? So if you see, let's say this is a odd number. Now if you apply the bitwise OR operator, okay, this is not one, this is bitwise OR operator basically, right? So like what I will get, if all these bits are 0, okay, we will not get all the 0. Bitwise OR says, okay, like 1 0 I'll get 1, 0 0 0, and 1 0 is 0. Basically any bit is 1, then I will get 1 only. Okay, now here like I am applying this basically 1 on this 0th bit, so I'll simply get 1. Okay, now if my number is 14, so here 14 is a basically even number, so this last bit will be 0. Okay, this we have seen in our first approach. So here with OR, okay, or you can say with 1, if I apply the bitwise OR operator, what I will get, because in the case of bitwise OR operator, if any of the bit is basically 1, then I will get 1 only, right? So here I am getting 1. Now here all the bits are 0, here all the bits are 1. Okay, so the same thing will go. Okay, if any bit is like 1, I will get 1. Okay, 1 0 1 1 0 1. Okay, this I got. Okay, now if we simply say ki, okay, number or 1, okay, number or 1 is equal basically 0, okay, then it is like even number, otherwise it is odd. Okay, I cannot do this. Okay, basically here you can see in both the cases, whether it is even or odd, I am getting a non-zero number. Okay, so this formula will not work. Okay, I will apply this same thing, but here I will check somehow in a different way. So here if you see what is happening, here if you see this is a 11. Okay, and here you see what is this number, this is number is again 11 only, right? Now in the case of even number 1 1 0, what I am getting, this is 15. Basically it is 1 greater than the my initial number, that is 14. Okay, this is incremented by 1, but here there is no incrementation. Okay, I am getting the same original number only, right? In case of the you can say odd number. Okay, if you apply the same thing on another odd number, let's say this is 3. Okay, 1 1 is 3. Now if you apply this mask 1, okay, on this, and you apply the bitwise OR operator, so 1 1 will, I'll get 1, again 1. So I got the same number in case of the if my number is odd number. Okay, so my resultant number and the initial number both are same, they are not incremented, but in the case of the even number, they are getting incremented. So this is the observation. Okay, in case of even number, my final number will be basically greater than the my initial number, but in case of the odd number, my resultant number and the initial number both will be same. The same program, it is written here, n or with the 1, if I am getting the number greater than my initial number, okay, then my number is even, otherwise it is odd. Okay, or you can write this way also, like if n or 1, okay, it is equal, like in case of the even number, I am getting the number incremented by 1. Okay, so it will be like n plus 1. Okay, this condition will also be suffice. Okay, it is also correct. The same, it is even number. If it is not fulfilled, then it is an odd number. Or you can write in the opposite way, like if n or 1 equal my original number, then if it is true, then my number will be like odd number. Okay, in case of odd number is remain unchanged. If it is not fulfilled, if it is false, then it is even. I hope you can run this program. You will find the code in the description below. Okay, let's move to the third approach. The third approach will be done with the bitwise XOR operator. Okay, so again here we have to see the property of the XOR operator. Okay, in XOR operator, I think you know that if both the bits are same, okay, like this is A, this is B, if both the bits are same, then we will get resultant bit as 0. If both the bits are different, then only I will get 1. Okay, this is how the XOR operator basically works. Okay, this is just for the recall. In case of bitwise XOR operator, we will get the observation that if we apply the XOR operator, same thing, okay, n XOR 1, if we apply the XOR operator on the, you can say this is, let's say, a odd number. Okay, on odd number, if we apply this operation, then we will get that our resultant number will be decremented by 1. But if this number is even, like 14 is an even number, and if we apply the same mask, okay, and same XOR operator, then we will get the our resultant number incremented by 1. It will be increased by 1. So basically it was 14, now resultant number becomes 15. Here in the case of odd number, the number was 11, but after applying the operation, I got 10. The number got decremented. Okay, so this will be same even for 3 also. Okay, even for 10 also, or any even an odd number. You can check by yourself also. Okay, so just you can see like this is 11, this is 001. So both the bits are 1, so this bit will become 0. Okay, because JOR operator says if both the bits are same, I'll say 0. Okay, because this 0001, this is like mask, this is like hard coded. So here you can see this is like hard coded. Okay, my number is just getting changed. Okay, now here 10, again 1000 and 101. So basically all these 3 bits will remain same, only the last bit, okay, will be the differentiating factor. So in the case of odd number, because this will be the LSB and this will be 1 always in the case of odd number, so this will become 0 always. And in case of even number, because this LSB will be 0 and this will be 1 always. Okay, so in that case it will become 1 always, and all the bits will remain same. So all the bits are remaining same in even number also, in odd number also, only the last bit is changing. And how they are changing? In even number, the this 0 is getting changed to 1, that is the value of the overall number okay, after the operation it is getting increased by 1. But in case of odd number it is getting decreased by 1. So this is the simple observation. Okay, if n JOR 1 equal the incremented number I am getting, then my number n is even, otherwise it is odd. Okay, now let's see the last approach. Now in this approach we will use the bitwise left shift and bitwise right shift operator. And how we will use? So basically again this is dependent on the same observation, that LSB bit of the, you can say, odd number is 1, and for the even number the LSB bit will be 0. Okay, and let's see how we will do that. So basically what I will do, on the given original number n, okay, I will first apply this operator. And what is this operator? This is like right shift operator. Whatever answer I will get from here, I will apply this left shift operator. Okay, left shift operator. So this is right shift and this is left shift. Okay, so let's say we take an example. For example, n is 11. Okay, and let's say what is the binary representation? 1011, and this is a odd number. Okay, it can be any even or odd number. I'm just telling you like how this will work first. Okay, so let's take the odd number. Now I will first apply this bitwise like right shift operator. So right shift means this side we have to shift. So this 1 will be lost basically. Okay, as you know in the right shift and left shift how it works. Okay, now this 1 will come here. Okay, this is like lost. Now this 0 will come here, this 1 will come here, and here it will be like 0. So this is the answer after applying this n right shift 1. Now on this answer I am applying this left shift 1. So now this number will be left shift by 1 place. Okay, so what will happen? This 0 will be lost, and again this 1 will come here, this 0 will come here, this 1 will come here, and what will come here? Again it will be 0. Okay, so this number I got after applying this whole operation. So if you see this answer and this 1011, this is my initial number, both are different, right? Now let's see another number which is even number. Okay, this is like an even number. If you see 1100, okay, this is the binary representation of 14. Now I am applying this right shift operator, okay, on this number. So this 0 will be like lost, then this 1 will come here, this 1 will come here, this 1, and then here it comes 0. Okay, now on this number which is the resultant number after this operation, I am applying this left shift 1. So left shift 1 means now shift bits this place. Okay, so this 0 will be lost. Okay, 0 is like going out from the left side. Okay, pushed out from the left side, and now this 1 will come, 1 will come, 1 will come, and this 0 will be like appended. Okay, so now this is the final answer, 1110. If you see, this is an even number, and this is the initial representation of 1100 for 14. I got the same representation after all the operation, 1110. This is same and this is same. So basically this is the observation. For even number, my initial number, that is this number, and the final number, that is this number, it will be same. But in case of odd number, my initial number and the final number, they will be different. Okay, they will be different. They can be incremented by 1, they can be decremented by 1, there can be difference of 1 or 2, anything, but they will not be same. This is the simple observation. Okay, so like what is the idea behind this, like how it is working. That is the main thing. Let's see. So if you see in case of even number 14, okay, like you say ki, okay, I am shifting like this side, okay, so this 0 will be lost. All these triple one they came here, all these triple one they came here, right? Now if we like shift this side, what will happen? These 3 bits again will come here, okay, at their original place, and here it will come 0. The same thing we are applying here, okay. What will happen? This 0 will be 1 will be lost in case of odd number, but this 1011 will come here. Now if we apply like this left shift, then these 3 bits will come here, and here it will come 0. Now 0 will always come, okay, whether it is a even number, whether it is an odd number, and whether it is an even number. The least significant bit of the final number will be like will become 0, okay. Now in case of even number, here the least significant bit was 0, here also we got 0. So that means whatever was there in the original number, I got the same in the final number as the LSB. But in case of the like odd number, here I got 0, but originally in my odd number this LSB is always 1. So both the number will remain different due to this LSB. Basically all the other things will remain same, here also, right, here also, but this LSB is the main thing, differentiating factor, okay. So same thing I have done, okay. First I have like created a final number, okay, by applying this operation, and if I say both final number and the initial number both are same, then my number will be even, otherwise it will be odd, okay. I hope you can run this program. You can find the code of these programs in the description below. So if you have any question, comment, suggestion, please write down into the comment box. And if you have any other approach to solve this question, please write down into the comment box. Hope you like the video. Please like, share, and comments, and subscribe this channel. See you in the next video. Till then, goodbye.